Around March 17th. Alright, let's do it. Oh, my legs is hurting. Let's get back to training. Deload is over. Longest nice subarray. I feel like I've done something similar before. You're given nums, all positive. We can call a subarray of nums nice if the bitwise end of every pair of elements that are in different positions in the subarray is equal to 0. We can call the subarray nums nice if the bitwise end of every pair of elements that are in different positions. So all the pairwise, that's a lot, right? All the pairwise, it's not a lot. It's if it have a length of n, that's just gonna be n minus 1 plus n minus 2 plus all the way to 1, right? So we want the bitwise end of every single pair is 0. Return the length of the longest nice subarray. The longest nice subarray. How do we check if everything pairwise is 0? I mean, we need to write the number out. For example, we have, I don't know, like maybe, what's 48? Don't know. 48. 1 1 1 2 3 4 0. 1 1 after 4 0. So 1 1 1 2 3 4. So it's 1 2 3 4 5 6. 4 5 6. Right? It's a 1. There's a 3. 8. Right? It's 8. 48. 10. That's 10. Okay, so 3 8 1 3 8 48 and 10. So in this case, 48 I can do anybody will be good. So maybe we should try to see which ones cannot be grouped together. Right, for example, 1 and 3 cannot group together. So yeah, this is the last is a 1. So all the ones at each position, right? So we just check at each position which ones cannot be together. So 1 and 3. So 1 cannot. 1 and 3 is bad. Right? Well, we can say bad pairs. Right? We have bad pairs. So 1 3 is bad pair. And 3 10 is bad pair because they're the same, right? And then 8 and a 10 is bad pair. That's it. That's all the bad pairs. So if we look at this thing, 1 3 8 48 and then 10, right? So we know bad pairs. So 1 3 is a bad pair, so we don't do this. And then 8 and 10 is bad pair. Right, so I cannot do 8 to 10, and I also cannot do 3 to 10. So this basically marked the smallest subarray that's not possible. Right, that's not possible. And anything including these are not possible. Okay. So if I want to say, give me the one starting from 1, I say if it's starting from 1, right? And I check, so 3, so I cannot include 3. So it has to be things before 3, but there's nothing before 3, so I cannot do 1. Start from 3, I cannot do 10, right? So the longest is going to be 3 to 48. 3, 8, 48, right? Starting from 8, I cannot do so. So starting from 8 is going to be 848. Starting from 48, I can do 48 to 10. Starting from 10, I can do 10 by itself. Yeah, Okay, so let's try the next one. So we have largest is 13. I think that's probably 4 positions. 1, 2, that's 3, 1. It's 5. Did you get 8 wrong? That's not 8, right? 4. 8 is here. This is 8. Ah, so in this case, this doesn't even exist. But it's fine. Because 8 to 10. And 8 to 10 also works. Yeah, I think 8 to 10 also works. Because that's 8. This is 1, this is 2, this is 4, this is 8. Yeah. It works as well. Anyway, we are here. This is 5. Alright, and 11. 11 is going to be 8 plus 3. That's 11. Right. And 13 is 8 plus 5. So, okay, so we have 3, 1, 5, 11, 13. So, last. Ooh, so nothing, right? No one. So what if you have like bunch of ones? So you have bunch of ones. You can actually go from there, right? Yeah, so it's like for each position, what is your maximum? So in this position, we have 3. In this position, we only have 2. In this position, we have now in this position, the second position actually have 4. And third position also has 4. Right? I have 4. Well, why the answer is 3? It's because you cannot. Okay, so I think you still need to find them, but if you find them at each position, I may have like this, a bunch of things. Which just means you cannot include Alright, change strategy. I think what I need to do is starting from the first one. I just need to find the first that has the first one that has the first one that fails. Right, so I have the current. I just need to find the first one that fails. How can I find it fast? Well, I know which position one. So I can say at the position 0, I have these at the position 1. I have these at position 2. We can just get what they are, right? So now, given my first number, and I know it's one position. Okay, so one position I'm going here, right? And now I try to find the earliest number, smallest number, larger than this. Oh, we could provide it as such, right? That is also 1. Okay, and then we find the next one. Yeah, I just go through here to see which one is the earliest that's bigger than me, that has this. And the next one, find the earliest. And then the difference between the two is the check, is the size. So let's start with, and now we go on to the next one. Okay. That, I believe, can work. Oh, but I need a data structure. It's a little bit complicated to do. Alright, data structure wise, I need to know what is the largest number. I don't know, but it's 10 to the 9th, right? So I can just set up a 32, which I think is fine, right? Just 32, and oh, we can get a maximum element. No, we can get a maximum element. But I don't think it's allowed, maximum element. So yeah, let's just get 32. Land 32. Or, no, or, let's just get 32. What do we call it? Set bits. Alright, for each one, we go from right to left. Oh, we do need the index though. Okay, index, so we say while n larger than 0, if n1 is 1, right? maybe I can just do this. And then I shall say set bits j is the jth bit dot pushback I and right shift 1 and j plus plus. Right, the next one, if it's not j also plus plus, we keep going until it becomes 0. Right, so we set this done. Okay, so that is to build the set bits. All we need to do is int rest equals 0. Right? Rest is 0. And then we go through them again one by one. Right, so say while n larger than 0, if n mod 1. Alright, so the current position is a 1, so I need to find the earliest, right, the earliest, so we say int index shall equal to upper bound, right, upper bound set bits j, where's j, set bits j dot begin set bits j and we need to find current I should be larger than this, right, this minus set bits j dot begin, so that's the index, right, pointing there. So basically what we're saying is the next thing that will cause us to fail, right? That's the index pointing to the next thing. So what we want to know is what is the maximum length that we can get, right? What is the maximum length we can get? So basically we need to check index. All right, we check index can get. So this is actually not a real index. Let's call it k. Okay, let's call it k. And the index relative to I shall equal to in the k is smaller than set bits j size, right? If it's smaller than that, then we can call it set bits j k. That's the index. That's the actual index. And I think what we can do is this one minus I. Otherwise, it's getting out, right? So that just means there's no more set bits on this. So it should be go to the end of nums. So we can just say nums dot size minus I, right? So that's that. So we have the index. That's not really the index. So k smaller than this, and then we do this minus. So that's the length, right? That's the size. So for each one, I need a current, and I want the minimum. So the largest should be in nums.size, right? That's the largest. So length is this, and say current shall equal to minimum current and length. Right. So if this, if not in 1j plus plus, right? So keep doing this. Right? If it's a 1, we look for the index and the set bits j, because we're looking at the jth bit, right? Looking at the jth bit, and then binary search will tell us at which position, right? And then we go to that position to find the actual index. Right? And if the actual index, or if we can find such a index, and then we use that index to get the largest length available just for that position, and then we find the minimum of all the positions. Right, so this one will give me a current, and when the current gets out, so res shall equal to min max, res, and a current. Okay, so once this is done, then we can return res. Have pretty good confidence on this one. I think we are hitting it right. List all the indices of nums, right, in order that has nums I at k position, right, as num I a set bit at k position. Then for any nums I, for any nums I, right, the longest subarray that allows it to satisfy, right, the condition for the bit at j, at position j, should be the distance from nums I to the smallest index in set bit. I feel like it's hard to explain. I think example will be easier. For example, given nums equal to, I think I can use this as an example. Right, 1, 3, 8, 48, 10. Their binary representation are 1, 48. And the last one is a 0, a 10. This is 8. This is 4, 2, right? I think this one's wrong as well. But we are redoing it, so it's fine. OP. Zero position is 1, 3. And at one position, it's 1, 2, 3, 4. At 2, 3 position 0, 1, 2. 2 position is nothing. 3 position 0, 1, 2, 3, 4, 2, 4. This is nothing because I only have 1, and this is nothing. Okay, so now we say we start from 1, then this is 3, so if your answer is 1. And start from 3, this one is infinite, which is just going to be 1, 2, 3, 4. Because 0, 1, 2, 0, 1, 2, 3, 4, 5. We say 5 minus 1. Right? 5 minus 1 is 4. And then the second one is just going to be 3. Starting from 3 is going to be 3. Okay, so here it's actually going to be 2. So, right, starting from, okay. Oh, I'm so sleepy now. Let's hope. Yeah, I think it should be right. Unless I think to make it easier, even easier to understand. 0. Alright, what's the runtime? ON. ON. This is ON. Within ON, we have log. Call it ON login. Call it ON login. Alright, let's see if we got lucky. Oh my god, we're not getting lucky. And I'm so tired, so this is gonna be bad. Oh. Print binary. And I remember if number 0 with b. So if I don't know. $32. Okay. So start from here. I say, oh, did I? Oh wait, hold on. My answer is 4. Oh yeah. So I need to also find the first if it's this, I think it's an else. Right? Else if it's equal to 0, then I need to find the second one. Right? The second for at this position. Right? At this position I have a bunch of ones. I have ones at this position, this position. So I need to search with my I. Right, so it's the same. So we say int. Okay, it's the same. Well, it's the same. Why don't we just do it outside? Right? If it's the same, so k. So k is just search for the current j. Right, the jth bit. The jth bit, and then we find upper bound. And now upper bound to find, again, we always find against I. Right, always find against I. And now which is better is the current is a 0 bit. Alright, so it's gonna be this plus 1. This plus 1. Yes, it's gonna be this plus 1. So we say int length shall equal to again case smaller than set bits j. If it's smaller, then I have a So we have something. Actually, no. If, should I say, if k plus 1 is smaller, then we say set bits j k plus 1, right? So k plus 1, that we have that index. So don't use that. So it's be this minus I. Otherwise, it's gonna be nums.size minus I. Because you know it's k plus 1, so we can just take the remainder. So now we got a length. I don't even need this. I can simply do this here. Okay, let's try it again. Length. Oh, 36 minutes. Come on. Let's get this one done. Let's get this done. Come on. There we go. Oh, I think they have set the time it's much more stringent now. I used to click this and then I can go for the other one. It should be fine. All right. Submit. Huh. Interesting. It's still not right. Okay, so what's the problem now? I already handled. I already said k plus 1, right? K plus 1, if it's smaller than this, so we have something, so we need to query that. Minus 1 minus I. So from here all the way to there is good, right? Otherwise it should be nums.size minus, so that's the length, and then you get the minimum length. Okay, so I don't see any apparent logical issue, but this one answer is output 4, expected is 3. Output 4, so is a 1, so this is gonna be 1, 2, 3. Yeah, this is a 3, because that's the maximum you can reach. Here we have but it doesn't matter, so 3. Right here, 1, 2, 3. Yeah, so the first one is just 3. Right? First one is 3. It's actually 2. It's actually 1. First is 1. Second is 3. Third is actually 2 because there's only 2. Fourth is 1. Fifth is 1, 2, 3. This one will be, oh, this one's a longer. 1, 2, 3, 4, 5, 6. This is longer. This position, long. This position is 1, 2. There's actually only 2, right? So in this position, actually 2. This position, 1. its position. Oh, this is the one. Starting from here. Oh. 1, 2, 3, 4. I say I get 4. Ah, that's not right. And stuff from here, I say I can get 4, but actually this is only 3, 1, 2. There's only 2 actually, yeah. There's only 2. Because I say from here to here. No, that's not right, because I will say here. So it's actually 1, 2, 3. This is 3. This is still 3. So starting from this 3, from here is actually only 2. Oh, also, yeah, 2. So start from here. Actually 2. Here's 1, starting from here is 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 1. Yes, where is the 4 come from? Right, where does the 4 come from? Okay, I probably... Yeah, where did the 4 come from? Don't know. I have some suspicion, so I'm going to try put a parentheses and see if this one works. Oh, it's not a parentheses. I'm gonna delete some of the other test cases and just focus on the last one. Okay, I basically want to see out length index I. So I have I length. Alright, let's see. Let's get the length. That's not right. I just get current. That shall give us an idea. Okay, 0, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1. Everybody's 1. 8. What the hell is 8? 0, 1, 2, 3, 4, 5, 6, 7, 8. Is not. 1, 2, 3, 4. 1, 2, 3, 4. Yeah, it's not. This position, right? This position is not. Because if I search, it will give me here, and a plus 1 will be here, right? So this minus should be 3. How do we get a 4? We can debug this. Oh, in fact, I can set. All right, we shall debug this. I have an idea of how to debug this. All right, so we do what's the function name? Longest. All right, longest, and then we debug. We can go the debugger here, and then this is we just start from 8 because it doesn't really matter, right? It doesn't really matter. So now what we're gonna do is when I C line this thing. Oh, this is 18. 3. There's also 3. Build it. Okay. Come back. F5. Domain. Okay, now we are doing. So we start from 8, which is fine. All right, it's 4. Right, that's 4. So current is 17, is fine, and larger than 0. So K. Right, set bits. J is 0. Okay, set bit 0 is this. Okay. So we I is 8. So if I do binary search, we're gonna get this. Alright. So it's gonna be 12. So it'll be 4. So K index is 4. Index is 4. 0, 1, 2, 3, 4. That is correct. And we do this. So this is going to give us K plus 1. Right. So 12 minus 8. So this will give us length is 4. Yes, length is 4. So current become 4. Okay, so now j equal to 1. So what we want to see is 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 basically. So length is 5. That will be big. Wait, we jumped out. Oh, damn. All right, now we saw. Oh, I completely did not consider this. Oof. Okay, so that is not right. Gosh. Well, at least we figured out the problem. So we're gonna say, oh boy, that's gonna be a for loop then. J0, j smaller than 32, j plus plus. Okay, so we have j. Yeah, we do this first. And here is what we want is mask. Right? What we want is mask. So we can say mask shall be 1 left shift j. Right? Yeah, this is a mask. So we shall say this is actually gonna be mask. Right? We do mask. Now we go through all 32 positions. Okay, and use bit manipulation and binary search. Alright, hopefully this time we'll get it. Yep, I think we're good. So let's bring back everything. We run again. Make sure everybody's happy. Oh my god. How are they not happy? 0. How is 0 even possible? What? How? How is 0 even possible? Oh, because I have another j++. Oh, I also have this. These are all not necessary. We actually, I think only use n once, so I can just do I. So I don't even need this. I don't think I use n again. Okay, let's try it. I don't understand. I don't understand. How come it becomes 0? I do binary search, the upper bound. And minus I. What? So maybe it's because all the zeros is messing us up. Maybe. I don't know. It doesn't feel right. If it's an empty array, what do we get? Maybe. I'm not sure. Maybe we should say what if it's an empty? It'll always give you the. Oh, what in the world? I think I'll try the second. Try the first one. Just kind of give an idea of what the length is. Right? I want to know what the hell is going on. Yeah, we have 32 times. We have, let's do I, length, alright, let's see. Curious. I didn't even run. Oh, I was like, what in the world? Why the stops working? Because for debug purpose, I made some change to the code and I forgot to change it back. That is really stupid. Come on, I gotta pass this time because I really can't hold on much longer. Yeah, there we go. Very bad. Okay, that's like ridiculously bad. Which means we have a much better solution. I just didn't know. Boy, now I have to really think. Basically, yeah, you go every Let me think. Sliding window? It has to be 1. Like each position can have at most 1 1. So we have a second one. Now we need to shrink. Maybe it's a sliding window solution. Yeah, I can see how sliding window might work. So let's see. It should be sliding window, I feel. Yep, sliding window, and it's added together, right? I'm not sure if it's added together. Use the bits. Tracks bits used in current window. Window and if current number shares bits with window. Used bits. And this is not so. Yeah, then we have a used bits. So we remove leftmost exclusive all, yes, because if it's the same, I should return 0. Try it. Is it equal to 0? Yeah, keep going. Once it's done, we'll add a current to the window, yes. Because we have no bits that's been used. Oh, wow. This is amazing. Yep, that's... Alright, we have to recall this one. It's not working, this one. Yeah, it's sliding window. Maybe we're back to the sliding